Okay, so in the previous video, we saw we had these fundamental equations, Vs equals ds dt. We had A equals dv dt, and we have ADS equals VdV. Okay, so all our kinematic problems can be solved using these equations. Okay, I want to remind you what is kinematics. We're just looking at the motion of the particle. What is kinetics? We're looking at the forces, what is causing the motion. So the motion is described again by our position, our velocity, and our acceleration. Okay? Now, a special case, right? These can be applied to any situation, okay? But if we have a situation where we have constant acceleration, note, if we have constant acceleration, right? For example, A is 10 meters per second squared, okay? Or 9,81 meters per second squared, or 10,000 kilometers per hour squared, something ridiculous like that. These are all constants, right? Okay. Then we can obtain the following equations, right? If we take, okay, we can find an equation that relates velocity to time. Velocity is a function of time, and this you would have seen from high school. If we take, which one is it? This. We take this equation. So we've got A equals dv dt. But we know that A is a constant. It looks like something like this. Then what we can do is we can solve for velocity, okay, by separating variables and integrating. So this is a constant. AC is a constant. It looks like that, 10, 9,8, whatever, dt. And we integrate dv. And we integrate between 0 and t and between 0 and v. Okay? And we're going to get here we're going to get a t, a constant times time, and we're going to get v. If we rearrange, this becomes v is equal to, sorry, this was between v and v0, okay? So this is going to be v minus v0, so this becomes v equals v0 plus at. Okay, I'm sure we've seen this one. So, again, if our acceleration is constant, then we can obtain a function that relates velocity to time. Velocity is a function of time, so we get v equals v0 plus at only if acceleration is constant. We can't use this equation if our acceleration is not constant. What does it look like if our acceleration is not constant? It might look like this: 12t meters per second squared. That's not constant, right? If you're looking at an AT at the curve, at the graph, then this will look like something like that. It's not constant. Or it could be 40t squared. Okay? That's not constant. It's going to look something like that. Okay? But what is constant? Something that looks like that. 10 meters per second. 4 meters per second. Okay? So now the next one we want to look at is position as a function of time. How do we get this? We use this equation that says v equals ds dt. And v, we just solved for v. V is this. So we say that is equal to v0 plus at. Okay. Then we separate variables because t is on this side. We separate variables. So we got ds between s0 and s is equal to the integral of v0 plus at. And this is between 0 and t. All right? So what does this become? This becomes s minus s0. That becomes v0t plus half a constant t squared. So this is S0 V0t plus half a t squared. This is position as a function of time. Position as a function of time. We can only use this if acceleration is constant. Finally, we can obtain velocity as a function of position. Velocity is a function of position. All right? So, what do we use? We can use this final equation, AdS equals VdV. So we've got AdS equals VdV, and our acceleration is constant, and then we just simply integrate this, and that's between S0 and S, between V0 and V. And if we remember, that's a constant. This is a constant. It's like 10 or 13 or 1,362,341.2. It's a constant. That becomes A times S minus S0. And on the right-hand side, we're going to get V squared over 2 between V and V0. So, which equals this, equals a half V squared minus a half V original squared. If we rearrange this, we are going to get this V squared is V original squared plus 2A constant acceleration, S minus S0. Okay? And that is velocity as a function of position. So we can only use these equations when we have constant acceleration. Okay? So the next couple of videos we will do a couple of problems. Okay? Cheers.